Hello and welcome to a lecture on the intrinsic properties of two ports. I'm Steve Ellingson and this lecture was recorded on August 4th, 2013. The intrinsic properties of two ports are those which apply when the input and output are terminated by the reference impedance or do not depend on how the ports are terminated. So here's an outline of this lecture. First, a brief review of two ports and S parameters, summarizing the previous lecture. I'll remind you about forward gain, which we also discussed in the previous lecture. Then I'll introduce reverse gain, insertion loss, reverse isolation, and return loss. I'll remind you about input and output reflection coefficients and emphasize that these are themselves intrinsic properties if we interpret them under the standard conditions. That's the input and output impedances equal to the reference impedance. Then I'll introduce the input and output impedance for these standard conditions. And then some examples to put all of this in context and to give you some numerical values for circuits that you might encounter. Three more properties. Reciprocity is one. The lossiness of two ports, whether they're considered lossless or lossy, and then this issue of whether two ports are unilateral or bilateral. I'll explain what that means and what the implications are. Before we get started, let's briefly review the last lecture so I can make sure that we're all on the same firm footing for the new material. We have defined a two-port as some linear circuitry which is accessed through two ports, so that its behavior is completely described by the linear relationships between just four parameters. We developed the idea of power waves, inbound and outbound from each port. These are A1 and B1 for port 1, and A2 and B2 for port 2, respectively. Then we defined S parameters as the coefficients which describe the linear relationship between these power waves, as shown in the equations on this slide. Finally, remember that all these values depend on the chosen value of the reference impedance, Z0, which is typically, but not always, chosen to be 50 ohms. We also found in the previous lecture that the S parameter S21 is the ratio of the outbound voltage wave from port 2 to the inbound voltage wave arriving at port 1. We called that the forward voltage gain of the two-port, since it describes the ratio of magnitudes of the associated voltage waves. We decided that S21 magnitude squared describes an increase in power, since the impedance on either side of the two-port is defined to be equal and equal to the reference impedance. So we call that the value of the forward power gain. Now in radio engineering, when we refer to forward gain without specifying whether it's voltage or power, we usually mean forward power gain, and that'll be my convention as well. Forward gain is a very important idea which has great relevance independent of S parameters. Let us now consider the definition of forward gain, which applies generally and is not specific to S parameters, just so you can see this concept. The forward gain of a two-port is defined as the ratio of the power delivered to a load equal to the reference impedance at port 2 to the power applied to port 1 from a source impedance Z0. And we found out that this turns out to be equal to S21 magnitude squared. And since we often work in dB, it's useful to provide an expression which gives you forward gain directly in dB, and that's just 20 times the logarithm base 10 of the magnitude of S21. Finally, it's useful to know that for two ports consisting of passive devices, the forward gain is less than or equal to 1. This is a consequence of conservation of power. For passive two ports, there cannot be any power delivered to the load which was not provided by the source. That's what it means to be passive. Obviously, for active two ports, such as amplifiers, you can have a forward gain greater than 1. It turns out to be useful also to define a reverse power gain or reverse gain for a two-port. This we simply call the reverse gain. The reverse gain of a two-port is defined to be the ratio of the power delivered to a load equal to Z0 at port 1 at the input relative to the power applied to port 2 from a source impedance equal to Z0, the reference impedance. And as you might be able to guess, the reference gain is S12 magnitude squared. Now this may be obvious, but regardless, I recommend that you attempt to derive this from the S parameter defining equations. We end up with a similar expression for reverse gain in dB as we did for forward gain. That is 20 log base 10 of the magnitude of S12, and that's the expression in dB. And we end up with the same observation that for passive two ports, the reverse gain has to be less than or equal to 1. And for the same reasons. Another metric that's commonly used to describe RF two ports is insertion loss. Insertion loss is frequently abbreviated just IL. The insertion loss of a two-port is defined as the ratio of the power applied to port 1 from a source impedance equal to the reference impedance Z0 to the power delivered to a load equal to the reference impedance at port 2. In other words, insertion loss is the reciprocal of forward gain, and thus insertion loss is equal to the magnitude of S21 raised to the exponent minus 2, or you could say it's minus 20 log base 10 of the magnitude of S21. Insertion loss must be greater than or equal to 1 for passive two ports. Now note that the forward gain and the insertion loss convey the same information. One is just the reciprocal of the other. So why do we have both terms? Well, this is purely for historical reasons. Forward gain is more commonly used to describe active two ports, like amplifiers, whereas insertion loss is more commonly used to describe passive two ports, such as filters and other passive devices. Yet another metric that's used to describe RF two ports is reverse isolation. The reverse isolation of a two-port is defined as the ratio of the power applied to port 2 from a source impedance equal to Z0 to the power delivered to a load equal to Z0 at port 1. That is, reverse isolation is S12 magnitude raised to the minus 2 power, or you could say minus 20 log base 10 of the magnitude of S12. That's the value in dB. Also, reverse isolation is greater than or equal to 1, that is positive in dB for passive two ports. So hopefully it's clear that reverse isolation conveys the same information as reverse gain. Again, there are historical reasons why we have both of these terms and why they're in common use. Another common two-port metric is return loss, which is abbreviated RL. The return loss of a two-port is defined as the ratio of the power applied to port 1 from a reference impedance equal to Z0 to the power reflected from port 1. And all this is happening under the standard condition that a load equal to the reference impedance exists at port 2. You can probably see right away that this is the reciprocal of the magnitude squared input reflection coefficient, that is S11. So why do we have this? Well, return loss is used to quantify the quality of an impedance match between the input port and the nominal impedance, which in this case is equal to the reference impedance. Also, is probably clear that return loss is greater than or equal to 1 for passive 2 ports. And unless it's indicated otherwise, when we say return loss, usually we're referring specifically to the input return loss. It is also possible to define an output return loss. This is pretty uncommon, so I won't give you a slide for that, but you can probably imagine what we mean by output return loss and what that's all about. Now a reminder that we've already identified some voltage reflection coefficients for the standard condition in which both ports are terminated into the reference impedance. We called these values gamma sub 1 and gamma sub 2, and they happen to be equal to the S parameters S11 and S22 respectively. Now you have to be careful. These are considered intrinsic properties of the 2-port only because they're defined for these standard conditions. So be warned, if the input or output terminations have impedances which are different from the reference impedance, Z0, then these are not the reflection coefficients that will actually exist. In that case, we'll talk about embedded reflection coefficients, and those will in general be different. In the previous slide, we identified the voltage reflection coefficients for the standard condition that both ports are terminated by the reference impedance. This suggests the utility of defining an input impedance for the same condition. We can derive this impedance in terms of S parameters using the general equation for reflection coefficient, that is the one I'm showing here, where Z1 is the impedance that we seek. That is the impedance looking into the properly terminated 2-port from the port 1 side. After just a bit of algebra, we find that Z1, this input impedance for standard conditions, is given by Z0 and depends also on S11, which is not surprising, through the equation shown here. Now you should make sure that you are able to derive this equation. And as you might expect, we can do the same thing for the other port, port 2. The output impedance, Z2, is the impedance looking into the properly terminated 2-port from the port 2 side. Not surprisingly, we obtain a similar expression for Z2 in terms of the reference impedance and S22. Now, before moving on, I'll warn you one more time. All of these parameters are defined for the standard conditions, that is, specific port impedances which are equal to the reference impedance. It is only in this sense that they are considered intrinsic properties of the 2-port. They are not necessarily the values that you actually get once the 2-port is installed in the circuit, because then the impedances seen by the input and output ports may be different from the reference impedance Z0. And in fact, this has a lot to do with why radio engineering is sometimes challenging and difficult. However, we will find that these intrinsic values that we've defined up to this point are quite useful when it comes time to design radio frequency circuits. They will appear as parameters and equations that we will use for design. Okay, now an example. In the previous lecture, we determined parameters for some very simple 2-port circuits. Here's the simplest circuit I can think of, just a zero-length continuation of the transmission line. In other words, the transmission line just continues through the 2-port. And here are the S parameters, which we derived or determined in the previous lecture. Now let's calculate the values for the various parameters that we have defined in the previous slides. Forward gain, reverse gain, insertion loss, reverse isolation, return loss, the input and output reflection coefficients, and the input and output impedances. I recommend you pause the video at this point and work these values out for yourself first before I show you the answers. So if you care to do that, please pause the video now. Okay, here are the answers. Note that the forward and reverse gain and the insertion loss and the reverse isolation are equal to 1, that is 0 dB. Hopefully that makes sense to you. Note that the is infinite. This is just saying that there is no reflection from port 1. On the right, we see that the input and output reflection coefficients are both 0, as expected, and that the input and output impedances are both equal to the reference impedance, and that's also as expected. Here's another two-port that we considered in the previous lecture, a disconnection between the input and output ports. No connection between input and output. And here are the S parameters that we calculated for this two-port in the previous lecture. So again, let's calculate the values for the various intrinsic metrics for this two-port. I recommend you pause the video now and work out the values for yourself first before I show you the answer. So go ahead and pause the video now. Okay, here are the answers. First, note that the forward and reverse gain are now equal to 0. And hopefully that makes sense to you. You could also say that the forward reverse gains are equal to minus infinity dB, but that's a little bit strange from an engineering perspective, so I've not bothered to indicate the dB values here. It's sufficient to say the gain is 0. The insertion loss and reverse isolation are now infinite, and this is just another way of saying that no power is transmitted through the two-port. That's not surprising since there's no connection between the input and output ports. The return loss is now 1 or 0 dB, and this is just saying that all the power which is incident on port 1 is reflected. On the right, we see that the input and output reflection coefficients are both 1, as expected. All the power has to be reflected. And that the input and output impedances are both infinite. Not surprising since they would appear to be open-circuited. Okay, here's yet another two-port that we considered in the previous lecture. In this case, a series impedance equal to the reference impedance between the two terminals. And here are the S parameters that we worked out to be true for this case. And then once again, let's consider the values or calculate the values for the various intrinsic metrics. So if you're inclined, go ahead and pause the video now and calculate those values. Okay, here are the answers. The forward and reverse gain for the two-port are less than 1. Specifically, the value we have is minus 3.5 dB. Now remember that the forward and reverse gain are always less than 1 for a passive two-port. So that's not surprising. The insertion loss is the insertion loss and reverse isolation are now greater than 1, and specifically the value is plus 3.5 dB. Remember, these values are reciprocals of each other, so that's not surprising. The return loss is now about 10 dB. It's much higher than it was for the previous examples, and that's just another way of saying that the match is getting much better. On the right, we see that the input and output reflection coefficients and the input and output impedances all have reasonable values. I say they're reasonable because, well, you could look at the circuit and independently of anything I've told you in the previous lecture or this lecture, you could probably get these values on your own. So they make sense. Okay. Here's an example that you can work out on your own, and that's the example of a shunt impedance equal to the reference impedance. I suggested you do this on your own as an example in the previous lecture, and I'm just continuing that here. So I'll not give you the answers, but hopefully you can work through this in the same manner that we've done the previous examples. And hopefully you can see from the examples I've just shown you that there's lots of ways that you can check your own work here. I'll just remind you, sanity checking your answers to problems like this is a pretty important engineering skill. So please take a crack at this and do your best to see if you can figure out whether your answers are reasonable or not. And I think I've shown you lots of ways that you can kind of check to see whether they're reasonable or not. Okay, now I'd like to show you three more intrinsic properties of some two-ports. The first property I'd like to talk about is reciprocity. So a reciprocal two-port is one which behaves identically when ports 1 and 2 are reversed. The behavior of a reciprocal two-port does not depend on which port is deemed the input and which port is deemed the output. So another way of saying that is that the indices of the S parameters can be transposed. S sub mn equals S sub nm. For example, S12 equals S21 for a reciprocal two-port. Or if you like to express the S parameters in matrix form, you could say that for a reciprocal two-port, the S parameter matrix equals its own transpose. All two ports that we've considered so far have been reciprocal, and this has been obvious due to their topographical symmetry. In other words, you can just look at them and visually imagine flipping them around 180 degrees, and you get the same circuit back. But there are non-reciprocal two ports, and they're important to know about, and we will encounter these in this course. For example, nearly all two ports that contain active devices are non-reciprocal, and that includes all amplifiers. Passive two ports containing non-reciprocal devices will be themselves non-reciprocal. So common examples of non-reciprocal devices include diodes, which allow current flow in one direction, but less so in the other direction, and ferrite isolators, which allow power flow in one direction and not so much in the other direction. The second property I'd like to address is lossiness. In other words, whether a two-port is considered lossless or lossy. So passive two ports can be characterized in one of these two, using one of these two words. In a lossless two-port, all incident power is either transmitted through the two-port or reflected. So another way of saying that is that the magnitude squared of the power waves B1 and B2 is equal to the magnitude squared of the power waves A1 and A2. And this is one of the strengths of S parameters, is that we can describe lossiness in this way. A lossy two-port is one for which some fraction of the incident power is dissipated inside the two-port. So then we know that the power associated with the outbound power waves, B1 and B2, has to be less than A1 and A2, which is the total power associated with the inbound waves. If the loss in a two-port is negligible for a particular application, we'll typically go ahead and consider the two-port to be lossless. Now, that just saves a lot of work. And in a lot of cases, it's much more complicated to deal with lossiness. If we can assume that it's lossy and that does not significantly affect our design or analysis, then it's usually to our advantage to assume that the two-port is lossless. And finally, I'll point out that this distinction between lossless and lossy two-ports is usually not meaningful for a two-port which contains active devices. The final property I'd like to address is the extent to which a two-port is unilateral or bilateral. So here's the deal. Often we prefer power within a two-port to flow in only one direction, that is from the input port, which we've been calling port 1, to the output port, which we've been calling port 2. When the source and load impedances are equal to the reference impedance, what this means is that S12 is 0. So a two-port having this property is referred to as unilateral. In other words, if a two-port has S12 equal to 0, we know that the reverse power gain is 0, and that's the condition that we refer to as unilateral. Most amplifiers are at least approximately unilateral. In other words, we like to see power flow from input to output in an amplifier, and it's usually upsetting to see power flow in the reverse direction through an amplifier. If not unilateral, then the two-port is considered bilateral, and that obviously means that S12 is not necessarily equal to 0. So, for example, most passive two-ports, that is, impedance matches, filter two-ports, will be bilateral. They work in both directions. All practical two-ports, in fact, will have a tiny bit of bilateral property. In other words, S12 will be not exactly 0, but it'll be maybe perhaps negligible, or maybe just small enough that its effect is small. This distinction between unilateral and bilateral two-ports will become particularly important when we consider the gain and stability of embedded two-ports, and particularly when we consider amplifier design. So when we get to amplifiers, these terms unilateral and bilateral will become very important. So the takeaway point here is a unilateral amplifier is one for which the reverse power gain is 0. That's S12 equals 0. This concludes this lecture on the intrinsic properties of two-ports.